2.
That's it. Yes, I will factor out a 2 and get 3x plus 1. Everything over 3x squared plus 2x minus 1. And this is it. What is this? The rate of change of this function at any point where this function is differentiable. Great. So now let's look at applications. So we know the technique. We know how to differentiate a log, a simple log, as well as a complicated log of a function. Any questions on this? Okay, so let's take a look. Let's start with advertising. So I think I'm on page 4. Yes, I'm on page 4. Let's look at 25. On page 217. Advertising. A model for consumers' response to advertising is given by N of A, which is 2,000 plus 500 natural log A. So this is the variable, and it's right here. And of course, they're telling us this is greater than or equal to 1. N of A is the number of units sold. Always take notes. Units sold. Okay. A is the amount spent on advertising in thousands of dollars. A in thousands of dollars. Okay. Part A. How many units are sold when $1,000 is spent on advertising? So A equals 1,000.
So would we just like plug it in and solve?
So they're asking us how many units are sold when 1,000 is spent on advertising. Just remember, A is in thousands. So they're really.
So A equals 1.
Yes, I should not write this. I should write A equals 1. Exactly. Very good. And I'm going to erase that. Good. So how many units are sold when A equals 1? And Mallory, you said what? To plug it in? Is that what you said? Because that's what we need to do. Okay.
Yep.
This does not even require a calculator. How much is natural log 1? Because we discussed that last time. We refreshed our memory on natural log 1.
Isn't it 0?
Excellent. How much is 0 times 500? Thank you, Rachel.
0.
And how much is 0 plus 2,000?
2,000.
Units sold. Part B. Very good. Find n prime of A, and then find f prime of 10. Good. So let's start. Can anyone help with n prime of A? Anyone? What is the rate of change of
first, wouldn't we first the derivative of 2,000 is 0, so
excellent.
We cancel that out.
Very good.
And then for 500 times ln A, it would just be, we'd use the product rule? What's it called?
This is a constant. We don't use the product.
Oh, it's a constant.
Yes. So a constant times a function is just a constant times the function prime. So natural log A prime will be 1 over A.
A.
That's it. So if you want better condensed 500 over A. Good. So now they're asking us to find f prime, to find n prime of 10. So when I plug in 10 here, which means A equals 10,000 actually, what do I get?
$50.
1 over 20? No, shit.
So that's okay. 500 over 10, 50. Now the measurement unit. I know.
Oh, because I tried to put it as thousands. I forgot it's only 10. Okay.
You will give me two measurement units, one for the top and one for the bottom.
Would it be $50,000 per unit?
So first, the y variable. What is the y variable measured in?
And is units sold?
Units sold. Very good. What is the variable a, or the x variable, measured in?
Thousands of dollars.
That's it. So always ask yourselves, what is y measured in? What is x measured in? And that's the rate of change. That is the measurement unit for the rate of change. Awesome. How much should be spent on advertising if 3,000 units are to be sold? Part C. How much should be spent on advertising if 3,000 units are to be sold?
So put 3 in for A.
3,000 units sold. How much should be spent on
Would we set it equal to 3,000?
Excellent. So 3,000 equals 2,000 plus 500 natural log A. What is our first step here? Great job.
Subtract the 2,000 over to the other side.
Absolutely.
And then divide by 500.
Very good. So then I have here 2 equals natural log A. And then how do I convert this into an exponential equation? Remember, the base here is e. E raised to the second power equals a. So e squared equals a. So a equals, and it has to be in thousands. So I'm going to share my screen. I didn't. I tried. Okay, I went directly to, okay. So we have here e squared. So that is 7,389.06. 7,389.06 thousands. I mean, it's 7,000. So maybe I should write it first at 7.389 thousands. Okay, final question here. Does it make sense to continue to spend more time on advertising? So in part D, they're asking us to find the limit as A approaches infinity from n prime of A. So from the rate of change. Okay, so the rate of change can be increasing or it can be decreasing. If it's decreasing, then we have to do something about it. If it's increasing, we're doing the right thing. So let's give it a shot. Where is my n prime of A is here, 500 over A. So this equals the limit as A approaches infinity from 500 over A. Can anyone give us this limit?
I feel like it would be negative infinity because as you got bigger, the amount coming out would get smaller.
But this approaches infinity. How come that a positive number over a positive number all of a sudden?
Well, okay, so not that'll be negative, but at least that I feel like it decreases, right? It gets smaller.
Good. So if
so approaches 0.
Exactly. Exactly. It's again the same idea. A tiny number divided by billions and trillions. It's 0. So the question was, does it make sense to continue to spend more and more on advertising? No, because the more you spend on advertising, you're still not changing this rate of change. So the more you increase, the rate of change becomes 0. So don't spend too much money on that beyond a certain point. Okay. Let's take a look at heating water. Any questions before we continue? So after heating water, let's look also at the population example, a problem, or anything else you want from this page, and we can start chapter 3. Okay, so at least 2 more problems we'll look at. Heating water and some population. So let's take a look. The time T in minutes. Always have this written down so you don't forget, because the measurement unit is important. Needed to allow a cup of cold water placed in a room to warm to T degrees Celsius. Okay, so T is in degrees Celsius. And we have T of T, so small t is in minutes, uppercase T is in degrees Celsius, and they are giving us this formula or function. 50 natural log of 15 divided by 25 minus t, where they say t is somewhere between 10 degrees Celsius and 25, but not 25. It cannot be 25. I just rushed to write the equal symbol, but it cannot be. Can anyone tell us why it cannot be 25?
It would be 0.
In the denominator, and that's not allowed. Yes, excellent, good. Okay, find t of 15 in part A. They want t of 15, which means 15 Celsius. And then they want us to find t prime of 15 and explain what each number represents. Fine. So this, very simple. Let's do it. I'll share my screen. I'll put in the function, because I may need it to plug in other numbers. So I'm going to put in 50, and then natural log, parentheses, 15 at the top, denominator in parentheses. The denominator must be in extra parentheses, minus x, close, and then close the outside. So the denominator inside here has to be in parentheses, and then so on and so forth. So for now, they're asking us to plug in 15. Fine. Here it is. Always highlight the number. So I see 20.27. So T of 15, 20.27. And remember, this is in minutes. So T in minutes, 15 in degrees Celsius. So we were asked to find the time that the temperature increases to 15. And what is the time? 20.27 minutes. Now they're asking us to find the rate of change of the minutes with respect to temperature when the temperature is 15. It's a totally different story, totally different measurement unit. Okay, so this is the function that we need to find the derivative for. Good. So t prime of t. Can anyone tell us how to start this? I look at a constant times a function, so I have to copy the constant. How do I differentiate this function?
Are we going to use first the product rule?
No, because this is a constant times a function. Only if I have 2 functions. I only have one. I have a constant times this function. How do I differentiate log?
Would it be 1 over a function times a function prime?
Exactly. So I'm going to copy now the function. times the function prime. Let's write it like this for now. Don't forget, we haven't finished. So it's 1 over the function times the function prime. I will flip this. So I have 50 times 25 minus t over 15, and now times. Because the numerator is a constant, I recommend changing the function, this piece in here, this function, as 15 times 25 minus t to negative 1. You can say, no, I want to use the quotient rule. Fine. That's fine too. Let's use the quotient rule if that's what you say. The denominator has to be squared. But see what happens now. You have to be very careful if you're using the quotient rule. What is the derivative of the top?
0.
Okay. So I have 0 and then minus. If you forget this minus, there is a problem. The numerator times the denominator prime, because this is 0. So once the derivative of this is 0 times the function from the denominator, I still get 0. And then minus. I copy the top and differentiate the denominator. What is the derivative of the denominator?
-1.
Brilliant, thank you. So that's why be careful whenever the numerator is a constant when you apply the quotient rule. Be very careful. Okay, so then I have, can I simplify here at least by 5? So I have 10 divided by 3 in front. I will definitely simplify one of these with one of these. I will multiply these two and I get 15. And I have over 25 minus t. I shouldn't even simplify because I would have missimplified the whole 15, but that's okay. And by 3. So I have 50 over 25 minus t. This is the derivative function. And in this, I want to plug in 15. So t prime of 15 is 50 over 25 minus 15 is 10, and this is 5. But I need the measurement unit, and I know you're going to give me 2 measurement units. The measurement unit of the y variable, of the measurement unit of the x variable. What is the y variable measured in?
Minutes.
Excellent. What is the x variable measured in?
Degrees Celsius.
That's it. So this is the rate of change by 5 minutes per degree. This is what is the value of the what time is needed when temperature is 15. Exactly just 20.27 minutes. That's it, period. But here, this is how fast is the time changing per degree. 5 minutes per degree.